topic. So if you'll take your notebook out from yesterday, I'll go back to the slide that we were on at the end of the hour, which is this one. Talked about how if Q is greater than K, that means that the reaction is product heavy, it's going to shift back to the left. If Q is less than K, it's reactant heavy, it's going to shift to the right. Good? Oh, you're clean. Good. Nice. That's an apple?
This is a crab apple.
That was peeled a couple weeks too early. Or picked off the tree. Yeah. Yeah.
It's like rock hard.
You're going to be puckering up because it's so sour. We're just going to watch it, Debbie. It's good? Oh. Just a little guy. Okay. Now, did you write this down from yesterday? Are we on it?
Yep.
Okay. Here's an example of a problem that we'll need to use this concept for. Will a precipitate form? Let's take a look at what we're given in the question. And this is in the homework. It's number 50. I don't know if it's assigned, but it's in the end of the chapter. At what pH will a 0.2 molar aluminum solution begin to show precipitation of aluminum hydroxide? Now you know that the K expression, KSP, is the product concentration over the reactant concentration. So Al plus 3 times the hydroxide concentration Q. It has to be written like this. Therefore, the reaction equation has to be written like this. Even though we're not starting with any solid. It doesn't say you're starting with solid. You're starting with the product. And does it go to the left? Will you see a precipitate form? I guess that's not the question. The question is, what does the hydroxide concentration have to be in order to see a precipitate? Can you see the board okay on your screen?
Yeah.
Yeah, I think that's a great idea. Now, we don't have any new concentration. We're assuming that the volume is not changing at all. So we're looking for this. If we're wanting a precipitate to form, that means Q needs to be greater than K. Let's take a look at this. We want to show precipitation, so Q must be greater than KSP. And therefore, what is Q? Q is found the same way that K is found. The Al concentration times the hydroxide cubed must be greater than the K value.
Would it be 3.9 for the coefficient?
No. I know that we have a 3 coefficient, but the 3 is there just to say what ratio those two react in. And it doesn't necessarily have to be that that has to be 3 times more than that, because the reaction's not going that way, it's going that way. So you can start with any amount of those two. They just react with each other in 3 to 1 ratio. So, if we know that the aluminum concentration is 0.2 molarity, times the hydroxide concentration cubed is greater than the K value, which we know is 2 times 10 to the negative 32nd. So what does the hydroxide concentration have to be? Well, it's like 0.2 times x cubed is greater than that, solve for x. It's not a pretty one that you can do in your head. You're going to wind up with 1 times 10 to the negative 31st power, and you need to take the cube root of that. Not equals, is greater than.
So you have to have it so that it's like it has the same ratio of or hydroxide
To the AL? No, you don't. Because again, the reaction, if the reaction is going to the right, however much of this you produce, you're going to produce 3 times that. But when it's going back to the left, they don't have to be necessarily in a 1-to-3 ratio in their amounts. They'll react in a 1-to-3 ratio, but you don't necessarily need 3 times as much of that as that. I mean, you don't just look at this and say, oh, if that was 0.2, you need 0.6 of that. That's not what we're doing.
so very, very small.
It's small.
Yeah.
So that's 4.6.
Yep, 4.6 times 10 to the negative 11 is the molarity of hydroxide. So what pH? Well, we have to find the POH and then change it over to pH. It's looking like 11, no, 2 point something?
Small. Shouldn't be only 1. 6 egg.
Yes, 1 sig fig is what we're stuck with because the K only has 1 sig fig. So we're going to round that to 5. So the pH, I'm banking on like 2 point something. Not banking, I'm guessing 2 point something. 3? Okay. Yeah, because the POH is 10, so 14, 10 point something, so it's got to be 3. 3.6? Okay. So the whole point is this. If you need a precipitate to show up, then Q has to be greater than K, so you're going to have enough information that you solve for one thing. Okay? That's not so bad. This concept, though, right here, be familiar with that and be comfortable with it.
Is that like a hint that the moon face added with that?
I didn't catch that.
Is this like a hint that's going to be on the test? Or
Well, yeah, it'll be on the test. It's not a hint, I'll just tell you that. All right, now here's something else. Not only do we want to know if a precipitate will form, sometimes we'll also need to know, okay, after the precipitate forms, what are the final concentrations of the ions? I'm going to give you a couple minutes if you want to write this down. This concept is going to be a little bit more work than what we've done so far this chapter. We'll do a couple of examples of this. One I'll do with you, and then the next one I'll have you try. So just take a moment if you need to write that down. I'll be quiet and let you write that.
just to rest that up against, so you don't have to hold it?
I think it's fine. I'll show you what I mean too about a modified ice table. It's different. How we doing? Everybody good with that? All right, let's take a look at an example of this, and I'll walk you through this. There's a lot of words on this, I know. We have two solutions that we combine together. So that means that some diluting happens first. Let's just take a look at this. I don't know if you'd like to write the whole problem out. It'll take a bit of time. A solution is prepared when you mix 75 ml of the barium chloride solution with 125 ml of the potassium sulfate. What are the concentrations of barium and sulfate ions in the solution? Is a precipitate going to be formed? And if so, what would make the precipitate? Should be pretty obvious. What's that? Yeah. And how can you tell? You know the solubility rules. How else could you tell? From looking at the screen. Well, no, we're not talking about dissolving something in acid. So it doesn't matter whether it's a conjugate of a strong or a weak.
Oh, no.
You're given the KSP of barium sulfate right here. The barium sulfate's got to be the precipitate. If the problem gives you what the KSP of something is, that's probably what they're after you making a precipitate of. Okay. But you're exactly right. You would have known that from the solubility rules. Good memory. Just like we were talking about in the last chapter as well. Sometimes the worst part of these problems is writing the chemical equation, knowing how to get started on it. Once you get started, you go through all the mechanics and it's fine. But this part, I'm going to make a huge suggestion. Always write the equations like this, even though this is not going to be intuitive. You have barium ions and you have sulfate ions, and you're going to be very tempted to say this. This would be the net ionic equation, and this is exactly what reaction is happening. So you want to write the equation like this. But you can't. What I have in the box, that's the form that the equation should look like. Okay, now, when we did chapter 4, we did the stoichiometry of precipitation. We wrote our chemical equations like this. One of them was limiting reagent. It went to 0. And we determined like how many grams of the product would be made, or that kind of question. That was when we were assuming that things could go to 0. Now we're dealing with the solubility of things that aren't very soluble. And it's really not true that something goes to 0 in its concentration, does it? You're always going to have a little tiny bit of it. So that means that we've got to consider the KSP. And I'm going to go ahead and erase this. It's not right. And we're going to write the reaction for the precipitate, the equation for the precipitation like this. This is not comfortable for us. Because we're not starting with any barium sulfate, we're starting with these two things. Why would you write that this way if you're only starting with products? Well, the reason is because it gives us the KSP. And what does a K expression include? It's the products over the reactants. So the way this thing is given, what they mean is barium concentration times sulfate concentration.